September 14th, 1944. Würzburg radar station, 12 kilometers south of Schweinfurt, Germany. Obergefreiter Klaus Hartmann stared at his cathode ray display screen as it dissolved into a blizzard of white noise, for 3 seconds, then 4, then 5. The carefully plotted green blips representing the American bomber formation had simply vanished, replaced by hundreds of false echoes that filled his screen like snow in a winter storm. "This cannot be electromagnetic interference," he muttered to himself, adjusting the tuning controls with practiced precision. The Würzburg FuMG 65 radar had been operating flawlessly since dawn, tracking the approaching bomber stream with its characteristic 7.4-meter dish. Now, at the exact moment when the Flak batteries needed targeting data most desperately, his radar showed him nothing but chaos. Through the concrete bunker's observation slit, Hartmann could see the Flak batteries begin their barrage. 88mm shells burst across the afternoon sky in random patterns, searching blindly for targets the gunners could barely see. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The distinctive drone of Pratt & Whitney engines grew louder as the American B-24 Liberators pressed forward through the defensive fire. But Hartmann's screen revealed nothing. The Americans had learned to make his eyes useless. What Hartmann did not yet understand was that he was witnessing the result of a technological revolution that had cost the United States over $15 million to develop and deploy. A revolution designed specifically to transform Germany's most accurate gun-laying radar into an expensive paperweight. The mathematical certainty of accurate flak fire was being systematically destroyed, not through destruction of the radar installations themselves, but through overwhelming their receivers with electromagnetic signals they could neither filter nor escape. The psychological impact would be devastating. German radar operators who had spent years perfecting their craft, who had guided flak batteries to hundreds of bomber kills, would watch helplessly as Allied jamming reduced their sophisticated equipment to static generators. The technological advantage Germany had maintained since 1939 was evaporating in a cascade of white noise and aluminum foil. The transformation had begun months earlier, but its origins reached back to February 1942, when British commandos had executed Operation Biting, the daring raid on a German Würzburg installation at Bruneval on the French coast. Major John Frost and his paratroopers had landed in darkness, overwhelmed the surprised Luftwaffe garrison, and extracted key components of the radar system. More importantly, they had captured radar technician Georg Huchel, whose detailed debriefings revealed the exact operating frequencies and design principles of Germany's primary gun-laying radar. The Würzburg family of radars represented German engineering at its finest. Development had begun at Telefunken in 1935 when Dr. Wilhelm Runge, the company's director of research, recognized that Germany needed accurate fire control systems for its expanding anti-aircraft defenses. The early Würzburg prototypes operated at 53 centimeters wavelength, using a 3-meter parabolic dish to achieve unprecedented accuracy for the era. By 1939, the Würzburg D model could track aircraft with azimuth accuracy of 0.2 degrees and elevation accuracy of 0.3 degrees at ranges up to 40 kilometers. But even the D model proved insufficient for direct gun-laying against high-altitude bombers. The solution emerged as the Würzburg Riese, the giant Würzburg, featuring a massive 7.4-meter dish mounted on a railway carriage for mobility. This system combined the proven receiver circuitry of the D model with dramatically increased antenna gain, extending range to 70 kilometers with accuracy of 0.1 to 0.2 degrees in both azimuth and elevation. This precision was sufficient for direct control of flak batteries without optical correction, making the giant Würzburg the cornerstone of Germany's radar-directed air defense network. By 1944, approximately 1,500 giant Würzburg systems had been deployed across occupied Europe, from Norway to southern France, from the Atlantic coast to the approaches to Berlin. Each installation represented a significant investment in materials and manufacturing capacity. Each required trained operators capable of tracking fast-moving targets while feeding firing data to flak batteries through analog computers called Kommandogeräte. Together, they formed an integrated defense system that Allied bombers encountered on every mission deep into German airspace. The Würzburg operated as part of a layered detection network. Long-range early warning came from Freya radar stations operating at 1.2 meters wavelength, with ranges exceeding 100 kilometers. When Freya detected an incoming bomber formation, operators would alert nearby Würzburg stations, providing rough bearing and range estimates. The Würzburgs would then acquire specific aircraft within the formation, tracking them with their narrow beam, while feeding precise position data to the Flak batteries. A typical integrated air defense site combined one or more giant Würzburgs with Freya early warning radar and multiple Flak batteries, usually consisting of 12 to 16 88mm guns. The Würzburg operator would track a single target, feeding range, azimuth, elevation, and rate of change data to the battery's Kommandogerät. This analog computer would calculate predicted future positions, allowing the guns to fire shells timed to detonate precisely when the bomber reached that point in space. The system worked with deadly efficiency when conditions were ideal. Through 1943, German Flak batteries using radar direction had maintained an average expenditure of approximately 2,000 shells per bomber destroyed. This represented a significant improvement over the optical fire direction used early in the war, which had required over 10,000 shells per kill. The radar-directed system gave Germany a fighting chance to defend against the growing Allied bomber offensive, despite overwhelming numerical disadvantage. But the Brunewald raid had revealed the system's critical vulnerability. British scientists at the Telecommunications Research Establishment analysed the captured Würzburg components with intense focus. They determined that the system operated at 53 centimeters wavelength, approximately 565 megahertz. More critically, they confirmed that the Würzburg used conical scanning, a technique where the radar beam rotated rapidly around the antenna's boresight axis. The target appeared strongest when centered in the beam. By measuring the modulation pattern of the return signal, the operator could determine which direction to move the antenna to keep the target centered. This elegant technique provided the accuracy Germany needed, but it also created a fundamental weakness that could be exploited through jamming. The development of Allied countermeasures proceeded along two parallel paths. The first involved window, British designation for what the Americans called chaff, thin strips of aluminum foil cut to half the wavelength of the target radar. When dropped in bundles from bombers, these strips would fall slowly through the air, each piece acting as an efficient reflector of radar energy. A properly designed window bundle would create a radar return equivalent to that of a large bomber, but thousands of bundles dropped along a bomber's flight path would create a cloud of false echoes that overwhelmed radar displays. Joan Curran, a Welsh physicist-engineer working at the Telecommunications Research Establishment, had perfected the window concept by early 1942. Strips measuring 27 centimeters in length, exactly half the Würzburg wavelength, proved optimal. Each strip was produced by laminating aluminum foil between paper backing, creating a durable reflector that would survive ejection from a bomber at high altitude. Testing confirmed that 6,000 strips weighing just 6 ounces would create a radar return equivalent to 3 bombers. Bundles dropped at 1-minute intervals would create a continuous corridor of false echoes that could screen entire bomber formations. The decision to deploy window generated fierce debate within the British government. Professor Frederick Lindemann, Winston Churchill's chief scientific advisor, argued that introducing window would inevitably reveal the technology to Germany, allowing the Luftwaffe to use it against British cities. The fear was justified. Both sides had independently developed chaff concepts, but had refrained from deployment out of mutual deterrence. The question became whether the potential reduction in bomber losses justified breaking the stalemate. By July 1943, RAF Bomber Command's losses had climbed to unsustainable levels. During missions to the Ruhr industrial region, casualty rates exceeded 7%, with German radar-directed Flak and night fighters accounting for the majority of losses. Air Marshal Arthur Harris concluded that window deployment could no longer be delayed. On the night of July 24, 1943, 791 bombers took off for Hamburg in Operation Gomorrah. For the first time, they carried bundles of window, with instructions to drop them at 1-minute intervals beginning at the German coast. German radar operators watched their screens fill with hundreds of seemingly identical returns. The carefully orchestrated system of ground-controlled interception collapsed as controllers lost the ability to distinguish actual bombers from clouds of chaff. Night fighters, equipped with Liechtenstein airborne radar, found their scopes equally useless. The radar-guided searchlight batteries that normally illuminated targets for flak and fighters wandered aimlessly across the sky. Hamburg's defences, considered among the strongest in Germany, fired thousands of shells blindly into the night. Only 12 bombers out of 791 failed to return, a loss rate of 1.5% compared to the expected 6 to 7%. The devastation continued for over a week. Successive raids dropped additional thousands of tons of bombs, while window rendered German radar defences ineffective. More than 40,000 civilians died in the resulting firestorm, and significant portions of Germany's second-largest city were reduced to rubble. The psychological impact on German defenders proved as significant as the physical destruction. Operators who had spent years developing expertise in radar-guided interception watched their skills become irrelevant overnight. The technological advantage they had wielded with such effectiveness had simply evaporated. German scientists had anticipated window, calling their version Duppel after the Berlin suburb where it was developed. But the mutual deterrence that had prevented British deployment had also prevented German preparation of countermeasures. Now, frantically, they worked to develop solutions. The most immediate response involved retuning radar sets to different frequencies, forcing the Allies to recalibrate their window dimensions. But this proved only a temporary expedient, as Allied reconnaissance quickly identified the new frequencies and production lines adjusted accordingly. More sophisticated solutions emerged slowly. The Wurzlaus modification introduced frequency diversity, allowing rapid switching between several preset frequencies. This forced attacking bombers to drop multiple types of window simultaneously, complicating their countermeasures but not eliminating them. Another modification, called Käthchen, attempted to exploit the Doppler effect, distinguishing between slowly falling chaff and fast-moving bombers by measuring frequency shifts. But the computational demands exceeded the capabilities of analog systems available in 1943, limiting effectiveness. The most successful German countermeasure proved tactical rather than technical. Oberst Hajo Hermann developed wild sow, or wild boar tactics, in response to Window's introduction. Single-engine day fighters would orbit above target cities, hunting visually against the illumination from fires and searchlights below. Ground controllers would direct fighters toward areas of greatest window concentration, knowing that bombers must be nearby. The technique achieved some success during late 1943, but it demanded exceptional piloting skill and placed day fighters in weather conditions for which they were not designed. Accident rates climbed nearly as high as combat loss rates. While Window created chaos for German radar operators, it represented only the first element of the Allied electronic warfare campaign. The second element, developed specifically to target the Würzburg gun-laying radar, emerged from the Harvard Radio Research Laboratory in Cambridge, Massachusetts. This laboratory, established secretly in March 1942 with funding exceeding $15 million, focused exclusively on radar countermeasures development. Under the direction of Professor Frederick Terman, who would later be called the father of Silicon Valley, the laboratory employed over 800 scientists, engineers, and technicians at its peak. The laboratory's most significant achievement for the strategic bombing campaign was designated Carpet, a tunable jamming transmitter specifically designed to overwhelm Würzburg radar receivers. The basic concept was elegant. Rather than attempting to jam all possible radar frequencies, Carpet would be tuned in flight to match the specific frequency of the Würzburg installation, guiding flak batteries toward the bomber. Once tuned, it would transmit high-power white noise centered on that frequency, overwhelming the relatively weak returns from the bomber itself. The radar operator would see only noise, making accurate tracking impossible. Developing carpet required solving several significant technical challenges. The transmitter had to be compact enough to fit within a bomber's fuselage without displacing bombs or fuel. It needed to cover the frequency range from approximately 500 to 600 MHz, encompassing the various Würzburg models deployed across Europe. Power output had to be sufficient to overwhelm the radar receiver from ranges of several kilometers, requiring careful attention to antenna design and transmitter efficiency. And the entire system had to be reliable enough for combat operations, functioning under conditions of vibration, temperature extremes, and battle damage. The solution emerged as the APT-2, the American military designation for the production carpet system. The transmitter generated approximately 100 watts of output power, using vacuum tubes specially selected for reliability under combat conditions. The antenna, carefully designed to provide coverage across the forward hemisphere, was typically mounted in the bomber's fuselage. Most critically, the system could be tuned either to preset frequencies before the mission or adjusted in flight using a companion receiver designated AN-APR-4, which detected and measured radar emissions. This capability to tune carpet in flight created the concept of spot jamming, a technique that proved far more effective than simple barrage jamming across all frequencies. A skilled operator using the APR-4 receiver could identify the specific Würzburg installation guiding Flak toward his bomber, tune the carpet jammer to match that frequency precisely, and overwhelm that particular radar while conserving power and avoiding interference with friendly systems. This technique demanded well-trained operators and added complexity to bomber operations, but it dramatically increased jamming effectiveness. The first carpet jammers arrived in England during spring 1944, initially designated for installation in lead bombers of each formation. The U.S. 8th Air Force began operational use on October 20, 1943, with disappointing initial results. The preset frequency approach proved insufficiently flexible, as German radar operators had become adept at rapidly retuning their systems when they detected jamming. But the introduction of spot jamming techniques in summer 1944 transformed effectiveness. Skilled operators could identify and jam the most dangerous Würzburg installations, forcing German flak batteries to rely on less accurate optical direction or simply cease fire altogether. The effectiveness of combined window and carpet jamming became quantifiable in loss statistics. During July 1943, before window deployment, RAF Bomber Command suffered a 5.8% loss rate on missions over Germany. By August, after window introduction, the rate dropped to 2.85%. For all of 1944, after window had become standard procedure and carpet jammers were widely deployed, the average loss rate to all causes fell to 2.3%. For 1945, it declined further to 1.4%. Window alone accounted for much of this reduction, but operational analysis suggested carpet jamming provided an additional 30 to 40% decrease in effective flak damage. For the American 8th Air Force flying daylight missions over Germany, the impact was equally dramatic but measured differently. Unlike RAF night bombers that faced radar-directed night fighters as their primary threat, American formations encountered concentrated flak over heavily defended targets. A November 1944 analysis by the 8th Air Force Operational Analysis Section documented that between 3,300 and 4,400 bombers returned with flak damage in each month from April through September 1944. This represented approximately double the entire first year of operations. The German defences were growing stronger, with targets that had been defended by 60 guns in 1943 now protected by 300 guns in late 1944. Against this intensifying threat, carpet jamming provided measurable protection. One bomb group using chaff and barrage jamming with the Carpet WWII variant reported a 2.55% loss rate to flak during July 1944, with 5.5% major damage. After spot jamming techniques were introduced in August, losses fell to 0.4% with major damage declining to 0.8%. While these figures reflected multiple factors, including changing tactical situations, they demonstrated that effective electronic countermeasures could significantly reduce casualties even against increasingly numerous defences. The US 15th Air Force, operating from Italy against targets in southern Germany, Austria, and the Balkans, achieved even more dramatic results. Against the heavily defended oil refineries at Ploiești, Romania, 4 bomb groups equipped for barrage jamming reduced their loss rates substantially compared to unprotected formations. The Ploiești defenses were formidable. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Multiple giant Würzburg installations worked in concert, each tracking different bomber elements while feeding data to numerous flak batteries. Aerial photographs taken during attacks clearly showed the integrated system, with Würzburg dishes visible, tracking the formation that photographed them while flak bursts filled the sky. By late 1944, all 8th Air Force bomb groups operated barrage jammers on every mission. Most used the Carpet 3 variant, a higher-powered version more effective at overwhelming Würzburgs operating across narrow frequency bands. Spot jammers were deployed in most groups across all divisions. The German response to this jamming war became increasingly desperate. Radar operators would search frantically for unjammed frequencies, only to have skilled American jamming operators retune and neutralize them within minutes. Often, German operators would simply shut down their radars entirely, waiting for the bomber formation to pass before resuming operations, essentially conceding that effective fire control had become impossible. For Klaus Hartmann, sitting at his Würzburg console south of Schweinfurt on that September afternoon in 1944, the implications were personal and immediate. He had trained for 18 months at the Luftwaffe Signals School at Halle, learning the intricacies of radar operation, target tracking, and fire control coordination. He had served at this station since February, successfully guiding flak batteries to several confirmed bomber kills during spring and early summer. He took professional pride in his accuracy, in the smooth coordination between his tracking and the flak battery's firing solutions. Now, his screen showed him nothing but noise. He attempted every countermeasure he had been taught. He switched between the preset frequencies, but each showed the same white chaos. He adjusted his gain controls, attempting to see through the jamming, but the American transmitters overwhelmed his receiver with power levels. His equipment could not filter. He tried narrow beam scanning, hoping to exploit his antenna's directivity, but the jamming appeared to come from multiple directions simultaneously as different bombers in the formation activated their carpet jammers. Through his headphones, he heard the increasingly frustrated communications from the flak battery commander. Without radar data, the battery was firing barrage patterns, saturating probable approach corridors with shells timed to detonate at estimated altitudes. This expended ammunition at a prodigious rate while achieving little. The battery commander could see the American formation with optical rangefinders, but the rangefinders provided insufficient accuracy for effective fire at 18,000 feet altitude. The shells burst in the general vicinity of the bombers, but no aircraft fell. Hartmann could see several B-24 seconds clearly through his observation slit, their distinctive twin tails silhouetted against the afternoon sky. They flew in their characteristic tight box formation, designed to maximize defensive machine gun coverage against fighters. Silver flashes erupted periodically from beneath the bombers as they dropped fresh bundles of window, maintaining the protective cloud of false echoes. He could see thin strips of aluminum foil glinting in the sunlight as they fell slowly toward the ground, each one acting as an efficient reflector of his radar's energy. The bombers pressed forward through the flak barrage, seemingly undeterred by the defensive fire. Hartmann knew their target, the ball-bearing factories at Schweinfurt, critical to German war production. Earlier raids on these factories had caused significant damage, but German defenses had been strengthened substantially. More flak batteries, more fighter squadrons, more radar installations, yet now, at the moment of truth, his radar showed him nothing useful. The Americans had found a way to blind him without destroying his equipment. The psychological impact extended beyond individual frustration. The entire German air defense system had been built around radar technology. Billions of Reichsmarks had been invested in research, development, manufacturing, and deployment. Thousands of personnel had been trained. Complex organizational structures had been established. And now, Allied countermeasures threatened to render this entire investment ineffective, not by destroying the equipment, but by making it useless through overwhelming electronic interference. The strategic implications were profound. Without effective radar guidance, German flak batteries reverted to the kind of blind barrage fire that had proved so inefficient early in the war. Estimates suggested that expenditure rates climbed from 2,000 shells per bomber destroyed to over 3,000 shells, with some analysts suggesting figures as high as 4,000 shells. This placed enormous strain on ammunition production and logistics. Each shell required copper for the driving band, steel for the casing, explosive filling, fusing mechanisms, and transportation. Multiply by thousands of shells per mission, by dozens of missions per month, and the industrial burden became staggering. German industry was already struggling under the weight of Allied strategic bombing, raw material shortages, and the demands of fighting on multiple fronts. The requirement to produce tens of thousands of additional flak shells monthly, while simultaneously attempting to match Allied aircraft production, tank production, and maintain basic military logistics, exceeded German manufacturing capacity. Resources diverted to flak ammunition were resources unavailable for other critical war materials. The choice became impossible: produce more shells to defend against bombing, or produce more weapons to fight the ground war, knowing that inadequate air defense would allow more damage to your industrial capacity. Personnel demands created similar impossible choices. By 1944, approximately 1.3 million men, women, and youths served in the Luftwaffe's flak forces. This represented a massive diversion of manpower from other military duties. Many positions were filled by older men in the Home Guard, Hitler Youth boys and girls, and even prisoners of war from Allied nations like Italy and Hungary after those countries attempted to leave the war. But skilled radar operators and fire control specialists required months of training and could not be easily replaced. Each time Allied jamming rendered a radar operator's skills irrelevant, it represented not just a tactical defeat, but a waste of scarce training resources. The German scientific community attempted to develop countermeasures, technologies that could defeat Allied jamming and restore radar effectiveness. Teams led by some of Germany's finest engineers explored numerous approaches. Frequency agility systems that would hop rapidly between multiple frequencies, faster than Allied operators could retune their jammers. Pulse compression techniques that would improve signal-to-noise ratio against jamming. Passive detection systems that would track the jammers themselves, potentially allowing fighters or flak to target jamming aircraft preferentially. Advanced signal processing that would filter chaff returns from actual aircraft returns. Several of these approaches showed promise in laboratory testing. The Mannheim Rieser, a giant version of the earlier Mannheim radar, featured a very narrow beam that made it relatively immune to window, though not to direct jamming. Only a handful were manufactured due to high production costs. The Ansbach mobile radar, introduced in 1944, attempted to combine range and accuracy in a mobile package, but arrived too late and in too few numbers to affect the air defense situation. The Jagdschloss ground-controlled interception radar, designed with a plan position indicator display, reached operational status only as Allied forces overran German territory. By November 1944, Allied intelligence teams investigating abandoned German radar installations found evidence of desperation. At Eisemont, in Belgium, an incomplete Jagdschloss installation revealed German attempts to deploy new equipment before Allied advances made it pointless. At Mars-la-Tour, investigators found an old giant Würzburg FuMG station in the process of being upgraded with incomplete Jagdschloss and chimney radar components. Local French workers reported the installation had been started in August, with planned completion by January 1945. It would never be finished. The end came in stages as Allied armies advanced across Europe. Radar stations in France were destroyed by bombing, overrun by ground forces, or simply abandoned as German garrisons retreated. The massive radar installation at Douvres-la-Délivrande, near Juno Beach in Normandy, with its multiple Freya and Würzburg radars, was blinded by intensive jamming on the night of June 5–6, 1944, hours before D-Day. On the morning of June 6, Allied naval artillery destroyed its antennas. The garrison held out for 12 days, supplied by nighttime parachute drop, before finally surrendering. Similar scenes played out across occupied Europe as the Reich contracted. For Klaus Hartmann, at his station south of Schweinfurt, the war continued through the autumn of 1944 into the winter. Each mission brought the same experience: careful preparation, initial detection of approaching bombers, then the sudden dissolution of his display into white noise as American jammers activated. Sometimes he could track targets briefly before jamming began. Occasionally the Americans made mistakes, starting their jammers late or tuning them inefficiently, giving him precious seconds of useful data. But these became increasingly rare as Allied electronic warfare crews gained experience. The bombers kept coming. The 8th Air Force's daylight raids grew larger, sometimes involving over 1,000 heavy bombers escorted by hundreds of fighters. The 15th Air Force struck from the south. RAF bomber command continued its night campaign, now augmented by window and sophisticated electronic warfare aircraft from 100 Group. The defensive response grew more desperate. Flak batteries fired blind, expending precious ammunition for diminishing returns. Fighter squadrons struggled against overwhelming Allied air superiority. Radar operators watched their screens fill with noise, while bombers destroyed the cities and factories they had been trained to protect. By March 1945, as Allied forces crossed the Rhine, the organized German air defense system had effectively collapsed. Fuel shortages grounded most remaining fighters. Ammunition shortages limited flak battery operations. Many radar installations had been evacuated, destroyed, or captured. Allied bombers roamed German airspace almost at will, targeting oil refineries, transportation networks, and industrial facilities with increasing precision. The Battle of Germany was ending, and the electromagnetic dimension of that battle had been decisively won by Allied technology and industrial capacity. The statistical accounting tells a story of technology overwhelming courage and determination. Allied bombing killed approximately 600,000 German civilians, destroyed vast industrial capacity, and diverted massive resources to air defense that might otherwise have been used on other fronts. German flak forces, despite their size and determination, could not prevent this outcome. In 1944 alone, flak accounted for approximately 3,500 American aircraft destroyed, while German fighters shot down 2,900. But set against the production capacity that manufactured tens of thousands of American bombers, these losses were sustainable. Germany's defenses were not. For the German radar operators who had served from the beginning, who had witnessed their equipment evolve from the primitive sets of 1939 to the sophisticated giant Würzburgs of 1944, the progression told a bitter story. They had seen technological superiority shift decisively to the Allies. They had watched as each German innovation was countered by Allied response, each countermeasure neutralized by Allied countermeasure. The cavity magnetron that powered Allied centimetric radar, the proximity fuse that made anti-aircraft shells exponentially more lethal, and now window and carpet, making German radar defenses effectively blind. The equipment remained physically intact. The giant Würzburg dishes still rotated on their railway mountings. The operators still sat at their consoles. The flak batteries still had shells to fire. But the system no longer functioned as designed because Allied electronic warfare had broken the chain of detection, tracking, and fire control that made it effective. German radar had been defeated not by destruction but by obsolescence, by the revelation that Allied technology had advanced beyond Germany's ability to counter it. The lesson would echo through subsequent conflicts. Electronic warfare had proven itself a decisive dimension of modern combat, as important as air superiority or naval dominance. The ability to detect without being detected, to see without being seen, to strike without being struck back, these became defining characteristics of technological superiority in warfare. The electromagnetic spectrum became a battle space as important as land, sea, or air, with victory going to nations that could master its complexities. For Klaus Hartmann and thousands like him, the war ended in surrender and occupation. His giant Würzburg was captured intact by advancing American forces and subsequently transported to the United States for detailed technical analysis. Its components would inform Allied understanding of German radar capabilities, contributing to post-war electronic warfare development. The operators were dispersed, returning to civilian life where their specialized military skills had little application. The expertise they had developed, the tactics they had refined, the victories they had achieved, all belonged to a conflict that was ending. The final irony was that German radar technology had never been inferior. The Würzburg family of radars represented engineering excellence, sophisticated solutions to difficult technical problems. German scientists understood electromagnetic theory as thoroughly as their Allied counterparts. German manufacturing produced equipment of comparable or superior quality, but understanding physics and building equipment proved insufficient without the industrial capacity to produce countermeasures in war-winning quantities, without the electromagnetic dominance to operate equipment free from overwhelming jamming, without the strategic depth to sustain losses while maintaining offensive pressure. The examination of captured German radar equipment after the war revealed not technological backwardness, but rather the practical limits of what any nation could achieve when fighting enemies who possessed superior resources, stronger industry, and unbreakable will. German engineers had built excellent radars. Allied engineers had built equally excellent jammers and produced them by the tens of thousands. German operators had refined their skills to high art. Allied electronic warfare crews had learned to neutralize those skills through overwhelming application of technology. The verdict was written not in technical manuals, but in loss statistics, mission reports, and the ruins of German cities. Klaus Hartmann survived the war and returned to his home near Dresden to find it reduced to rubble by RAF Bomber Command's attack in February 1945. He found work eventually, rebuilding and teaching, though he never spoke much about his service. Years later, in a brief memoir written for his grandchildren, he recalled that September afternoon, when the American B-24s pressed through his racer, Flak battery's defenses while his radar screen dissolved into white noise. He remembered the frustration, the helplessness, the knowledge that his skills and his equipment had been rendered useless by an enemy with capabilities he could not counter. He remembered understanding, in that moment, that Germany had lost not just a tactical engagement, but the technological war itself. The mathematics were irrefutable, the physics were unforgiving, the strategic implications were inescapable. They returned from their radar consoles and their flak batteries, carrying knowledge that their finest equipment and bravest efforts could not overcome the electromagnetic advantage Allied science had created and Allied industry had, deployed in war-winning quantities. They fought on because duty demanded it, and hope dies slowly. But they knew. The blinding of their radars had shown them the future, and the future belonged to an enemy who could make them fire blind. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.